learn new things. So my name is Palak Patel. I'm working in the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, Civil Engineering Department. I'm going to teach you the design of structures, and subject code is 3150612. This subject in a third year, SEM 5th in civil engineering. So in this lecture, we are start to learn Unit 3 limit state design for RC structural elements. So in this lecture, we learn which element is singly RC beam. So shall we start? So here the first is the definition of beam. Beam is a vertical component of the building which gives a support to a slab. These are the beam definition. Now what is a singly beam? So singly beam is the main reinforcement are only in a tension zone. Only in a tension zone. So in the previous lecture I explained एक second, hold on students. I think okay, yeah. Previous lecture we discussed about a beam, the compression zone and tension zone. In the neutral axis video, neutral axis lecture. So here is a compression zone in the top portion and tension zone in the bottom portion. So your reinforcement, main reinforcements in the tension zone. So this type of beam we call as singly reinforced beam. Understood? Simple singly reinforced beam design and construction is simple, but sometimes singly reinforced beam are not preferred to construction than doubly reinforced beam design and build. So there is a singly reinforced beam design is so simple. So simple, design and construction is so simple, but sometimes it will not prefer. Sometimes this type of singly beam reinforced beam, singly RC beam, is not preferred to construction. So by that time we have to construct or build a doubly reinforced beam. Understood? There are some more type of beam. First is simply supported beam. In a simply supported beam, we have an end which are free to rotate and have no moment resistance. In a simply supported beam, we have a sub end is free to rotate and have no moment resistance. Means there is a simply supported beam, we have an end or hinge support or roller support. So this type of two support we call a simply supported beam. First is fixed beam, second one is so fixed beam we have a both end are fixed. Both end are fixed and restrained from rotation. And restrained from rotation. We call it as a fixed beam. Then after cantilever beam. In a cantilever beam we have one end in a cantilever beam we have one end is fixed and other end is free. We call this as cantilever beam. Second is overhanging beam. Overhanging beam where is a beam extended beyond its support on one end. You can see here is your beam. Yes, is one support, here is second support, and these are the extension portion. So this type of beam we call as a overhanging beam. T-beam. In a T-beam, we have a look like this type of slab here, okay, and in the slab we have a beam, okay. These are the structure, but in every time we have beam and slab are constructed monolithically. Both are constructed at the same time. So while we are constructed beam and slab at the same time, some portion of a slab, some portion of a slab is used for resist bending moment. Some portion of the slab which connected with a beam, which connected with a beam is is used for resist some bending moment. So at that time, this whole structure, this whole structure look like a alphabetically T shape. So we call this as a T beam. Simple definition is a T beam. Second one is inverted beam. So in an inverted beam, these are the slab here, okay, and your beam is above of the slab. In a regular beam, we have a slab, and the bottom of the slab we construct a beam. But in an inverted beam, slab in the bottom portion and beam on the top of the slab. And this type of beam used where a portion of slab is not in use. So this type of beam is not in common use. Okay. These are the two simple beam definition and type of beam by design. First of a singly reinforced beam. Singly reinforced beam with the reinforcement bar only in the tension zone. We discussed it earlier. And steel only carry a tensile strength. Second one is doubly reinforced beam. In the doubly reinforced beam, reinforcement bar at a tension zone and compression zone. At that time, steel carry tensile strength and compression strength both. These are the uh, design types of the beam: singly reinforced beam, doubly reinforced beam. Okay, understood? Then after some requirement, IS 456 2000 requirement. So this is effective span LE. Effective span for the simply supported beam, we have a two condition: clear span plus effective depth, or center to center support. Clear span plus effective depth, or center to center support, whichever is smaller. These are the two conditions here, 1 and 2. Whichever is smaller, we got a two value by this. Here called A, here called B. These are the two values we have by this two condition. And by these two condition, which value is smaller is used as an effective span. Understood? For the continuous beam, is depend on the width support. If width support less than 1 by 12 into clear span, then effective span is taken as a simply supported beam. Clear span divided by 12 and this value is more than width of support, then we have to follow these two conditions. We have to follow these two conditions. Understood? Second condition here. If clear span divided by 12 is less than width of support, or width of support is more than 600 mm, these both are same condition. While we have this both condition, we have to follow this rule. End span with one end fixed and other end continuous. or for intermediate span, we have effective span is equal to clear span. Effective span is equal to clear span. And for the end span with one end free and other continuous, one end free and other continuous, at that time clear span plus d by 2, d means effective depth by 2, or clear span plus 1 half into width of discontinuous support, into width of discontinuous support. Which support? This support, discontinuous support. By this value, whichever is smaller, we take this effective span. Understood? It's little bit take time for the understand. In this first condition, look here. Here is your slab and it's fixed at the both end. And we divide by beam. Okay. I have explained by this slab. Explain this condition by a slab. So look at here. Here is your slab, one end fixed, other end continue. So this condition 1 here, I call is 1, here is 2, here is condition 1, and these are the intermediate span. So here also condition 1, and these are also condition 1. So by this one condition, we have effective span is equal to clear span. And if I can say this, here is your slab and divide by 2 beam, one end is fixed and other is free. At that time, these are condition 1, these are condition 1, and these are condition 2, because this end is free and other is continue. Understood? Cantilever beam. For the cantilever beam, effective span is equal to length to the face of support in plus one half into d, one half length to the face of support. Means in this condition we have a beam like this, okay, and here is a support, here is support. So length to the face of support, here is face of support and here is its length of face support, divide by d, effective by 2. So L plus d by 2, L plus d by 2 for the cantilever beam. Understood? Then after cover to reinforcement, why we provide a cover? Provide a cover for the protect of steel reinforcement from corrosion. Protect a steel reinforcement from the corrosion. So here you have two definition of cover reinforcement. First is nominal cover. We call it as clear cover. In a nominal cover, the thickness of concrete from the surface of reinforcement bar, from the surface of reinforcement bar to the nearest edge of concrete is called nominal cover. So look at here, it's a beam cross section. We have a two reinforcement here. Then surface of reinforcement is R, the surface of reinforcement. And from the surface of reinforcement nearer edge, look at here, these are the nearer edge, these are the nearer edge, and between these two difference we call it as a nominal cover. Okay, simple reference here. Now what is the effective cover? The thickness of concrete from the center of bar to the nearest edge of concrete is called effective cover. So here is a bar, we have center of bar from the nearer edge of concrete, we call this as effective cover. Simple. Both definition is so simple, you can understand easily. One is from the surface of reinforcement, second is from the center of bar. For the nominal cover should not be less than the diameter of bar. These are the IS code provision. We can find it from the IS 456 2000, page number 46, clause number 26.4. We can find it. Then after spacing of reinforcement, then spacing of reinforcement shall not be less than this value. Horizontal distance, for the horizontal distance shall not be less than these values. So what are the value? The diameter of bar if diameter are equal, the diameter of the larger bar if diameter are unequal, or 5 mm more than the nominal maximum size of coarse aggregate. 5 mm more than the nominal maximum size of coarse aggregate. These all three values are given in IS 456 2000, page number 45, clause number 26.3. By these three values shall not be less of this value. Means your spacing of reinforcement will not be lesser than these three value. Understood? Then after minimum vertical distance shall not be less than three values. First is 50 mm, 2/3 of nominal maximum size, and maximum size of bar. These are the three values. Then after maximum distance between bar in a tension, maximum distance in a bar in the tension. So for the tension zone, we have to find IS 456 2000, page number 46, table number 50. In the table number 50, we give the spacing in mm. For the maximum distance between a bar and the tension zone, we have to follow table 50. Understood? Then after maximum spacing of shear reinforcement, these are the spacing 0.75d or 300 mm. Whichever is smaller, it's called maximum spacing of shear reinforcement. By these two value, whichever is smaller, we take it as a maximum spacing of shear reinforcement. Understood? Its D is the effective depth. D is always a effective depth, small d. Then after requirement for a slab, requirement of reinforcement for the slab. Here is a beam. Requirement of reinforcement for a beam. So what is, look at here, there is a minimum tensile reinforcement. For the area of tensile reinforcement, we have an equation. This equation is given in IS 456 2000, page number 48, clause number 26.5.1. This equation is given in this IS code. You can find everything. Then after maximum tensile reinforcement, for the maximum tensile reinforcement is 4% of total cross section area of beam. It will be not more than 4%. Maximum tensile reinforcement. Maximum compression reinforcement, both values here, 4% of total cross section area of beam. Both values are same. Then after side face reinforcement, whenever wave depth is exceeded 750 mm, if depth of beam is more than 750 mm, then we have to provide a side face reinforcement. Okay, understood? If more than 750 mm, then require both side face reinforcement. Then the spacing of side face reinforcement, first is 300 mm or wave thickness, whichever is less. Look at here, 300 mm, 300 mm. If side face reinforcement spacing is 300 mm, so what is the value of, look at here, I am provide a side face reinforcement here. So this two value is, here is 300 mm, here is 300 mm, overall 600 mm there. Understood? Simple logic is here. So that's why we have, when weight depth increase 750 mm, then we have to provide side face reinforcement. Shear reinforcement. The shear reinforcement, we have the value equation here. ASV into B into SV is equal to 0.4 into 0.87 into Fy, minimum shear reinforcement. So what is shear reinforcement? Shear reinforcement is used for the resist a shear force. In the beam, we have stirrups. We have stirrups, which called as shear reinforcement, which used for the resist a shear force or bent up bars. Okay, these are the equations. Write it down in your notebook. You can find it from the IS code also. Okay, shear reinforcement. Then after beam design check for the cracking, you have to follow table number 50. These are the first check for the cracking. Then after check for the deflection. For the deflection, we have to find this allowable length by depth ratio. Allowable length by depth ratio. These are the 20 into modification factor. So by the modification factor, we can find it from the IS 456 page number 38 figure 4. By the figure 4, we can find a modification factor and multiply by 20. We found the allowable length by depth ratio, and these are the actual length by depth ratio. So actual length by depth ratio is less than allowable length ratio. That means your structure is okay. Your structure is good to resist deflection. Then after check for length development length. So this equation is given in the IS 456 page number 2000, page number 44, clause number 23.2.3.3 C. Very lengthy. Okay. Look at here. Length LD should be less than 1.3 into M1V into L0. So M1 is a moment resistance, 50% of steel at support. Whichever steel you provided, you have to ensure 50%. And V is a shear force at support. L0 is sum of anchorage beyond center of support. Sum of anchorage bar beyond center of support. How to find L0? L0 find a D or 12 into 5. D is effective depth. 12 into 5. 5 is the provided diameter of bar, reinforcement bar, which provided in the beam. Take a smaller value of these two. Take a smaller value of these two. Okay. So by providing this value, LD, we have find 5 into sigma s into 4 into tau b BD. So sigma s we have find by 0.87 into Fy. Phi is the diameter reinforcement bar and tau b is shear force. Understood? By this value, provide all the value, we have to require this equation, this phenomena we have to follow. Okay. So by when this equation will be fulfilled, your design will be okay. Means good. You design is check for the development length. Then after second definition is lever arm. So lever arm means this is a distance between the line of action of resultant compression and the line of resultant tension. So look at here. Compression, these are the tension. This is a graph of stress diagram. I hope you will watch my earlier videos so you understand this easily. So here is a graph look like this. It's a straight line, it's a compression area, and these are the compression force and these are the tension force. So between these two, there are two compression and tension force. These two distance is called as lever arm. Yeah, lever arm. So at the depth of n by 3 from the compression edge, when the n is the depth of neutral axis. So these are the compression edge we assume as n by 3. So n is the neutral axis. N is the neutral axis. By n by 3 we can find the resultant compression force force point. Resultant compression force point. But the resultant tension is at the level of reinforcement. At the level of reinforcement, here is provided reinforcement. At the level of reinforcement we found a resultant tension, and by 3 we found a resultant compression, and between compression and tension force distance we calculate a lever arm. Understood? Simple. Then look at the equation here. Lever arm is equal to A plus D minus N by 3. How can we find? Look at here. Here is a graph of cross section of beam. These are the reinforcement bar. We keep effective depth. At n by 3 we found a compression force. So here is a compression. Here is a tension. So between these two different distance we found a lever arm. So by this d minus n by 3 we found this area. So d minus n by 3. And find by some expression coefficient alpha 1 we found this equation d minus 0.42 xu, this equation for the lever arm. Understood? Then of the moment of resistance. Moment of resistance for the single beam. This is a resisting moment offered by a beam section to resist a bending moment at the section. Moment of resistance means how much moment your beam can carry. If you design a beam and try to analyze your beam, you have to find a moment of resistance. Moment of resistance means your design beam, how much moment your beam can carry. We call this as moment of resistance. Simple. So moment of resistance. Moment of resistance means a total compression or total tension into lever arm. Total compression or total tension into lever arm. We call this as a moment of resistance. So here is the equation here. 0.36 FCKB into XU. And here is the lever arm equation. Its lever arm is compression equation. Compression is only by a concrete, so FCK. Compression force is only resisted by a concrete, so FCK. T will become out, then you found this equation 1 minus 0.42 XU divided by D. Look at here, its D is come here. Okay. Then after divide by D, then we have to divide by D, we have to multiply by D. So by this we can say that is your equation is multiply D by D. and then after the multiply by d we got this equation. Understood? Then simplify some equation. 0.36 f xu upon d 1 minus 0.42 xu upon d into fck bd square. These are some simple simplification. And then after substitute xu is equal to xu max for find mu limit. For find mu limit. Why we provide xu is equal to xu max? Simple logic, look at here. What is xu max? Xu max is a maximum depth of neutral axis. So what is the maximum depth on neutral axis? Maximum depth on neutral axis means the depth when your structure can be fail can be failed. So at that depth we call as xu max. At the depth of neutral axis we call as xu max. If you want to list in the detail, you just watch my previous videos, okay, and you can understand what is xu max and what is xu, and I give learning a mu limit. So these are the equations we provide. Xu is your xu max upon d. For Fe250 bar we have a xu max is 0.53 d. So provide this value in this equation, 0.53 d. Look at here. And why after provide equation value 0.53 we got this mu limit 143 fck square. So by this equation I can say if I provide Fe250 bar, my moment limit is mu limit is 0.148 fck square. And for Fe415 bar, xu max is 0.48 d, 0.48 d. So after provide 0.48 d, we get the equation is here 0.138 fck square for Fe415 grade of steel. Understood? And for the 500 bar, Fe500. So Fe500 xu max is 0.46 d. Provide a 4.46 d in the equation. So after simplify equation and we got a value is 1.148 fck square. 0.134 fck square. These are all the equation. And for the moment resistance for the steel is a total tension zone. For the total tension 0.87 Fy AST into D minus 0.42 XU. These are the equation. XU provide XU equation is there. After analyze the equation, this all value become a 1. All this value become a 1. Look at here. Then after we take out a D from the take out a D. So these are the equation. You can see for the moment resistance of the tension zone. For the tension zone. Okay, students, we stop our video here. In the next lecture, we discuss about some equation and start analyze some beam, analyze singly RC beam and the design beam. So I hope you understand all the thing, and we will meet